So welcome to Physics 4480 and 9480, which is the PhD variant. Essentially, the topic which we're going to cover are the same for the two variants of the course. And what I want to do now is to give you a quick overview of where you find the material and where you can find exercises, projects, etc., etc. And I also wanted to say something about the practicalities and how we're going to organize the semester. Now, the official website of the course is actually the one you can find by searching for Phys 4480, and you just search for that one, and that will bring you immediately to the course. And you have the English variant here. You just click on that one if you're not familiar with the UIO, the University of Oslo setup. And what you will see then is obviously a link to this specific semester. And since I know that we have many students from outside the University of Oslo, one of the things which is convenient is actually to subscribe to the schedule. So if you look at the schedule here, you can actually subscribe to these activities, and then you can get a message either via email or by cell phone, whether there are changes in lecture hall and so on. So we will permanently move the lecture hall from this room in the chemistry building, which doesn't have the right capacity either. And also it misses some of the audio-visual equipment, which we would like to have. So we will be at the Center for Computing and Science Education, which is in the 4th floor in the eastern wing of the physics department. So what you will find here, when you look at the schedule, you will find links to the lecture video, which will be uploaded after the lecture. You will find other information, links to lecture notes, etc., etc. So the aim today is actually to give you an introduction to the course and also show you where we have the teaching material. So if you go back here and you scroll down the page, you will see that I actually started to record the lectures, and I know that you most likely have problems finding the other room, and this is actually a much more pleasant place. So I'm just recording, and we are just going to give you some basic information about where you find things here. So the teachers here, it's me. This is me, Morten, and then Stian will also help us with exercises. We have a university system called Canvas, where you can hand in the projects which we have. So these are like 2 midterm exams. And then you will find messages like moving to the new lecture hall, as you can see here, the Zoom link, which many of you have found already. And then I assume that if you come from the University of Oslo, that you're pretty familiar with Git as a version control software, and GitHub and GitLab, Bitbucket and so on as providers, where you can actually upload your files. So these are repositories. And there is a main GitHub link where all the teaching material is included. So you can actually download everything from that. So let me just show you what that one looks like. I will keep using the official website. I will put messages and so on, but these messages will also be included in a weekly mail, which I will send to everybody. So the weekly mail will include updates and a reminder of what we did the week before, and links to reading assignments and the material which you can look up. So the information will be both on the official website. You will get an email, and then you also have the main teaching material will be in these GitHub links. So if we go to that link, you will find something which looks pretty boring, not very exciting. It contains, as you can see here, the README file. It contains some instructions. It contains some notes about practicalities, textbooks, etc. So we will use in the beginning, there's a textbook by Zabo Noslund, and there is a textbook by Shavit and Bartlett, which are much used in this type of many-body physics. The textbooks are books which you can also find if you go into the doc folder. And if you scroll down, you will find a link which is called literature. And by some odd reasons, these PDF files, they just ended up there. I don't know how they came there. They just ended up. So the book by Sabo Noslund is actually a pretty good book, and there are solutions to the exercises as well. So I will follow the first chapters in the beginning, because that deals with some reminder on linear algebra, some basic mathematics connected with that. And it contains also a decent description of some of the basic ingredients when you define the basis sets, what we call a computational basis, etc., etc. So this is the kind of website or the link where you can find most of the information. So if you go back then, there is also a link which I'm continuously updating, and that is a Jupyter book. So Jupyter book is actually a collection of my Jupyter notebooks, and it becomes like a kind of mix between the weekly lecture notes and a textbook. So it's not a textbook, but it's something which tries to approach a textbook. And that's why I also give you the links to these books if you want some more reading. But many people can actually, they are self-sufficient with the material you find here. So that's a Jupyter book. You have, if you go back, you will also find a link to the weekly teaching material. And the material there is typically the material I will link to, but you will find the same in the Jupyter book. But in the Jupyter book, there's going to be a little bit more text. So it pretends to be a textbook, but don't take it too seriously. But hopefully it can guide your reading. Now, the weekly material is what I normally will try to cover. And I'm going to use a mix of using my tablet and the slides. And to slow down the pace when we are doing derivations, I will typically use the tablet, which then functions like a blackboard. And you will get the notes on the tablet, which will be my blackboard notes. So if I were to teach in a standard way with a blackboard, these will be the blackboard notes, and you will have them as a PDF file. So what you will find when you when you go into this GitHub address, if you go into the doc folder, you will also find a link to something which is called the handwritten notes. And this will be the blackboard notes or the whiteboard notes. I will link these at the official web page of the University of Oslo every week. But you will also have access to them immediately from this folder here. Now, if you then go back to the GitHub, the main GitHub address, you can download everything. If you're familiar with GitHub, GitHub is just a provider. It was a company before it was bought by Microsoft, and it's a repository where you can save your files. And I like to use it because it allows me to render, as a public or accessible for everybody, my lecture notes. And the fun thing, I often get the mails from people scattered all over the world, and where they tell me they've been using them and they want to know how to cite them. So it's it just follows my basic philosophy that knowledge should be freely accessible. That's just me. Not everybody agrees with that, but that's perhaps the only political statement I'm going to make. The other thing I wanted to do now is actually to give you a quick overview of what the course is about. And to do that, we are going into the weekly slides. You will also find a link to the weekly slides on the main Jupyter book at the end. So the nice thing with a Jupyter book is it's fully searchable. Are you guys familiar with Jupyter notebooks? Jupyter, yeah, a little bit. Cool. But this is just to give you a feeling of where you can access the material. And you can download everything if you want. So if you have Git or you're using GitHub, there is a graphical user interface which allows you to just download it. You can, with a simple command, you can do a Git pull and you can get the latest update. Or if you want to develop this as your own material, feel free to do so. We have often people who use the lecture notes as their own lecture books, electronic lecture notes. And then you would fork the material, because then you can update the material and have it as your own material. If you just do a download zip, you get the material as it is now, but you won't be able to get the updates because you haven't linked it with Git, which is a version control software. And some of you may have heard a story I like to tell. So having version control software installed allows you to keep track of changes you've made to files. And you can always reconstruct the file. So Git is a software which has an excellent manual, by the way. And it has what it does is that it keeps track of the changes to text files. So if you save a figure, a JPEG figure, and you make a new variant, it will save that one as well. If you save an executable, which is a binary file, and you make a new one, it will save that as well. And these can be big files. So you have to be a bit careful with what you save. So a Git file is typically, it operates on an ASCII file, and it keeps track of the changes. So it doesn't save the file, but it saves the changes. And then you can go back to a date when you saved the file, and you can reconstruct the file as it was that specific day. And that can be useful if you're programming and you had a program which was functioning well, let's say 10 days ago, and then you made changes and it doesn't function anymore. Then you can go back to the version which was functioning and try to retrace what went wrong. It's also a very good practice, and the story, as I said, which I like to tell, I guess Jonny has already heard that one. It's about, we had a master student who was sitting on the train, writing on the thesis on the laptop, went to the restroom, came back from the restroom, and somebody stole the laptop. And that person lost 3 months of text editing on the thesis. So that person actually got an extension for the master thesis. But having this kind of backups on essential files is something which is extremely useful. And it's very good if you want to collaborate on the projects. And so, but before we move on now, I just wanted to switch to the slides and just give you a quick overview of what the course is about and some practicalities before we then go into a repetition of linear algebra and some essential formalism for quantum mechanics. So if you go into this, we are going to cover methods which are important for condensed matter physics. And I know that many of you are actually dealing with condensed matter physics. If you're dealing with atomic physics, if you're dealing with quantum chemistry, which is actually atomic physics, molecular physics, and more, and nuclear physics in particular, and also other fields of condensed matter physics and material science. If you're dealing with nanotechnology or quantum computing, this course actually gives you a kind of basic overview of central many-body methods. That means methods for solving either Schrödinger equation, which is going to be the emphasis here, or Dirac's equation for many interacting particles. So we are going now to go through some of the basic concepts which we need. And then when we're done with that, we are going to start with the calculations of expectation values and other quantum mechanical properties which we're going to need. So the lecture notes will contain in the beginning, there's going to be an introduction, as I said. There will be some basic definitions, mathematical functions, and mathematical say methods which are appropriate. So quantum mechanics is heavily linear algebra based. So you will see that we begin with linear algebra. And since we are going to focus mainly on fermionic systems, there's also the possibility with bosonic systems. The fermionic systems are a little bit more difficult because you have the anti-symmetry. And that leads to the introduction of a determinant as an ansatz for the wave function of a many-body system. And that determinant has a name after Slater, who was the first one who introduced it, in order to include the anti-symmetry. That's not the solution to the interacting many-body problem, but it can be the solution of a simplified many-body problem. So when you bring in a interaction between particles like the Coulomb interaction or the strong interaction, then there are very few cases which can be solved analytically. However, we have single particle problems which can be solved analytically. And then you can build an ansatz for the trial wave function, which has the anti-symmetry, based on a single particle basis. So we are going to look at what this means and why we do that. So we are going to set up a computational basis, and that computational basis is the one which we can use as an ansatz for solving a many-body problem. So of the many-body problems we are going to look at, the many-body problems like full configuration interaction theory, which is, if you can diagonalize a matrix, it's essentially a matrix diagonalization problem. It's an eigenvalue problem. This is conceptually the simplest many-body problem. And if you can diagonalize in that space you're living in, then you have the solution to the problem. However, you know that we are actually discretizing a continuous problem, which means that we will have an infinite basis set. And the matrix which we should diagonalize should be infinitely large. This is normally reduced to a tractable dimensionality. And that tractable dimensionality means that we have made an approximation. And I'm coming back to the two main approximations we are going to make here, because they will actually influence how we understand different many-body methods and how we understand the error we make when we leave out something. And in some cases, we cannot quantify the error. In many of these traditional many-body methods, you cannot quantify the error when you make approximation. So that's a drawback. So we will move then to another method, which is called Hartree-Fock theory. And some of you may have heard of density functional theory. Density functional theory is widely popular in condensed matter physics. And it's a mean field theory, which allows us to actually deal and solve many-body problems. And then we are going to so-called post-Hartree-Fock methods. So we produce a mean field basis, and that is used in more advanced many-body methods like many-body perturbation theory, for people doing quantum chemistry and also nuclear physics. Something like copper cluster theory is widely used. So these are some of the things we are going to look at as many-body methods. And we are going to dive into what's normally called second quantization. So second quantization is a kind of misnomer because that gives you the feeling that there are many different ways to quantize. But second quantization is actually a transformation of your system to a system where you only keep track of the number of particles you have in different states. It means that you leave out the spatial degrees of freedom and other selected degrees of freedom, and then represent these in terms of integrals, which you have pre-calculated. So this gives a very compact formalism, and it is also formalism which allows us to introduce physical interpretation of the systems, which are very, which help in demystifying some of the complexity of a quantum mechanical many-body system. So second quantization leads also to things like Wick's theorem and ways to simplify the calculation. So this is a technicality which we're going to deal with. If we get time, I will show you how you can actually transform the second quantization operators. You will transform your Hamiltonian into this new way of representing it, and you can actually retransform it in terms of Pauli matrices, which is called a Wigner-Jordan transformation, which then allows you to prepare a Hamiltonian for quantum computations. So there are many small bits and pieces which have links to many different applications. So these are the things we want to visualize in the beginning here. And there are technicalities which will keep us busy the next month, roughly, before we move into more studies of physical systems. And then we have FCI, which is full configuration interaction theory, which essentially means that you diagonalize a problem. So you set up a Hamiltonian matrix, and then you can diagonalize. And if you can diagonalize, then you have an answer because you get all possible eigenstates of the system. But that means a considerable approximation, and it is limited by the size of the matrices you can diagonalize. Then we move into mean field theories, and we will keep an eye mostly on Hartree-Fock theory, which is a kind of kitchen item. So it uses the variational theorem, and it gives you a better single particle basis. And then with a better single particle basis, you can then use that one as a new starting point for more advanced many-body methods. So essentially, a mean field is that you reduce a complicated many-body problem to a set of coupled single particle problems, where each particle sees a field, a mean field, an average field, which is set up by the other particles. So if you think of an atom like neon, you have 10 electrons, which are the relevant degrees of freedom. And then each electron sees a repulsion, which is set up by the other 9 electrons. And then you can reduce the many-body Schrödinger equation down to a set of coupled single particle equations, which are easier to solve numerically. And the variational principle tells you get a better variational minimum and presumably a better starting point for constructing a single particle basis. So this is the next thing we're going to do. So we start with FCI, which is the method if you can diagonalize the matrix. If not, you will have to use approximative methods like many-body perturbation theory. We have copper cluster theories. Monte Carlo methods are actually covered by physics 4411. So all these methods reflect some kind of mathematical algorithm. If you think of FCI, when you can set up the Hamiltonian matrix and you diagonalize it, then you have a diagonalization problem. So you're actually rewriting Schrödinger's equation for many interacting particles as a diagonalization problem. If you look at mean field theories, these are coupled integral equations, differential integral equations. And essentially what you end up from a computational point of view is to solve iteratively a set of coupled differential and integral equations. So that's the mathematics behind mean field theories. If you do many-body perturbation theory, that is a Taylor expansion around an energy. So essentially, it is that, if you look at this from above, but clearly you have tons of small details which you need to fill in. But the mathematical algorithm for many-body perturbation theory is a Taylor expansion around the energy you're searching. And then copper cluster theory is actually an approximation to FCI, but where you rewrite the full diagonalization problem as a coupled set of nonlinear equations which are solved iteratively. So this is also the same as you have in the mean field theories. So iterative solvers are very popular in many-body physics. We are not going to cover Green's function theory because Green's function theory is the same as you rewriting Schrödinger's equation in terms of a matrix to be inverted, in terms of what's called the resolvent. So Green's function theory is essentially matrix inversion at the end. So then you have another mathematical algorithm. And Monte Carlo methods are just stochastic rewrites of Schrödinger's equation, where you solve an expectation value in terms of an integral, and that integral is solved stochastically because it has such a high dimensionality. So all these methods you will hear about, and when you meet the practitioners, they will obviously tell you my method is the best possible one. But all these methods have their pros and cons. So FCI gives you all the states which you have defined, and the eigenstates, but it's limited by the dimensionality. Hartree-Fock is a mean field, and it doesn't include all possible correlations due to the forces you have. So that's an approximative method. Many-body perturbation theory has a drawback that we don't know whether it converges. There is no kind of proper way of assessing that except for some simpler cases. Copper cluster theory in its standard form is non-variational, which means it can converge from below or from above. And you don't know whether it converges or not properly. So many of these methods have the problem that you cannot assess the error properly. Monte Carlo methods, on the other hand, are very easy in the sense of assessing the errors. But you need to have a good trial wave function. And the other thing is that the Monte Carlo methods, when you solve it with using diffusion Monte Carlo for fermions, then your wave function is the distribution of random walkers. And you have a diffusion equation in imaginary time. So it looks like a diffuse. So you rewrite Schrödinger's equation as a diffusion equation in complex time. The problem is that the distribution of random walkers is a positive definite quantity, whereas for fermions, it changes sign. So that leads to, in Monte Carlo methods, what you call the fermion sign problem. And that's actually one of these cases. If you solve that one, there is a party in Sweden where you meet the Swedish king, which you may attend if you solve that problem. That's one of the hot problems in lattice quantum chromodynamics, quantum field theory, and in all kinds of many-body physics, because Monte Carlo methods can, in principle, if you simulate long enough, give you the exact ground state. So many of these methods target the ground state because they use the variational principle. But it means also then that you have to labor a little bit extra to get excited states. Full configuration interaction theory, diagonalization problem, gives you all the states within that space. So every method has its pros and cons. And this is something which we are going to try to illustrate and explain to you during the course here. We have advanced courses like Physics 5419, which covers quantum computing. And also we have the Monte Carlo methods are more dealt with in here. And then we have Monte Carlo methods with machine learning, which is one of the big topic nowadays. And where you can actually show that you can get results which are at the level of diffusion Monte Carlo, which is the benchmark for many body theories, with a neural network replacing the trial wave function. So there is a lot of research going on. Some of the fields which are very important are actually, and this is something for those of you interested in more master thesis topics, it's time-dependent many-body theory. Some of you may have heard of time-dependent density functional theory, time-dependent Hartree-Fock theory, because you want to study the time evolution of a system under the influence of some external probe. So these are things which we will not cover here. There's a limit to how much we can put into 10 credits. So we will mainly stay with the 6 first bullet points, and then you see that there are connections with other courses which we have here. The textbooks, as I said, you have access to them through this in this literature link, and I will follow in the beginning this textbook by Szabo and Oslo, and I will send you small reading assignments every week, or not assignments but suggestions. That's a better word. So we are going to have 2 kind of midterm exams, and these are graded, and you get feedback, and they count 60% of the final grade. And then we have a final oral examination. And what we have done in that final oral examination is that what we have done with the 2 midterms of projects is that they try to cover most of the material. And what people have normally done is to use these 2 and make a presentation. So you would typically make a presentation of something like 30 minutes, and then we will question for another 15 minutes, and that's the final oral examination. So there will be no kind of nasty questions about this and that and derivations, but you will prepare a talk, a seminar, normally based on the 2 projects which you have worked on. That takes away a little bit of the stress with an oral examination. So today, we're actually going to look at some basic things. And I wanted just to quickly remind you of some essential properties here. But I think we can take a small break now because we are at the hour. So we just stretch legs a little bit. So this was about the practicalities and where to find the information and what the course is about. So these many-body methods are actually essential for understanding quantum mechanical systems of relevance in material science, nanotechnology, semiconductor physics, condensed matter in general, atomic, nuclear, quantum chemistry, molecular physics, etc. And you always end up dealing with many-body problems. So I suggest we take a small break, and then I will try to remind you of some of the basic linear algebra. So I will use the slides, but then I'm going to try to break the monotony by diving into the tablet as well. Okay. So welcome back. There are some small questions which we had in the break about the projects and deadlines. So the two projects, we haven't set the deadline for them and when we are going to deal with them. But typically what we have done is to have the project number one, the first one, defined for the first half of October. So a typical deadline could be around the middle of October. And then the second one has normally been in roughly the second half of November. Now for the oral examination, this is something which we agree upon among ourselves. And we just find a date typically in December when it fits. That's a typical situation. And what many people have preferred is actually to have the exam here after they've done with the other courses. And then often they'd like to have a little bit more time. So we've typically ended up with something like the 15th to the 20th of December as a possible time. But this is something we can discuss among ourselves when we want to have the exam. So we are pretty flexible here. And also, for those of you who know me, I mean, I've always been very flexible with deadlines because we know something always happens. And we are more interested in your insights than just stressing you with a fixed deadline. So all my deadlines are soft deadlines, except that when we have the oral examination, we need to be there, right? That's it, because we have to have an external examiner. Okay, so send me also, in case you have constraints, suppose you're traveling for an experiment, or you are busy with a workshop or school or whatever, then just let me know so we can always adjust these deadlines. It's often a problem when you do an experimental thesis that you have to be present at the experiment, and then you have to be there all the day. So what I wanted to say a little bit now is about what I'm going to define as basis states. And this plays an important role here because we need to define what we will call a computational basis, which we will use in order to make a many-body basis. And often we try to find a single particle basis, and we use that one to build a many-particle basis. That's the kind of basic strategy if your interaction is weak. If you're dealing with strongly interacting systems, this kind of approach breaks down when you have a single particle basis. If a single particle basis is a meaningful approach, then, and which is the case with many of the physical systems you can study with some of these many-body methods, then it makes sense to define a single particle computational basis, and from that one, build an anti-symmetrized wave function as a basis, and use that one as a starting point. That means that we need to remind ourselves a little bit about linear algebra. And typically a vector is something which you would, a state vector would be something which you write like this, but we like to use this Dirac notation, this bracket notation. So when I write this, it actually means this. I guess this is something basically everybody's familiar with. This is just to remind you of some basic things. And just take a look at the things which you have here. And next week, I will also have some exercises linked to this kind of basic linear algebra applied to quantum mechanical systems. Then we have the transpose, or this is actually the Hermitian conjugate of the vector, which is then simply given by this vector here. And we know that we have the inner product, which is defined as this quantity which you see here. And I do the numbering from 0 to n minus 1. You could start with 1 and end at n. I mean, that's just defining a new starting point. And this is done often because when you write programs in Python and C++, the first element is element number 0 in an array. And then you have, if you have two arbitrary vectors with the same length, then you have this general expression here. So this is some basic things which you probably have seen. And you note as well that for two different vectors, this product here is in general not equal to x times y. And there's a simple example here, which you can actually see down here. And if you take this vector here and take a similar other vector, you may actually see when it's a complex one, as a complex entries, you will see then that it's not the same. And if you then assume that x is given by a complex number, then you know that the inner product, it becomes like that. That's a real number. The inner product is always a real number. And you can use the norm inner product to normalize a vector. And I guess this is something which you also have seen before. So if you have two vectors, if you consider these two vectors which you have here, then you see that the inner products, this one is equal to -1 plus I, which is not the same as that one. And that leads to a rule which you probably have seen in quantum mechanics courses, which simply tells you that if I take this expression, that's the same as the one you have to the right-hand side, the complex conjugation. So just keep these things in mind. With inner products, we are in general dealing with complex states, but in some cases, for some simpler basis, which we are going to deal with, we are going to have a real function. But that's more an exception. Then there is something else which is very important in quantum mechanics, which we use repeatedly, and that's the outer product. Have you seen that before in linear algebra? This becomes very important because it defines operators which act on states, and you can have things like a projection operator, which is also very important. And you will see that again and again in this course. So the outer product of two vectors gives you a matrix. You've met the Pauli matrices. These are important matrices, 2 by 2 matrices. And sigma x and sigma y and sigma z, they are the fundamental ones. And sigma z has actually eigenstates, which we can define in terms of a state, a spinor, 1, 0 and 0, 1. So these are the eigenstates, but they are not the eigenstates of sigma x and sigma y. That's also important to keep in mind, especially when you want to dive into quantum computing, because then the eigenstates of sigma z is normally used to define a computational basis. What you will see here is some of the basic properties of Pauli matrices. When you square them, you have an identity matrix. And this is also important for some of the other properties which we're going to deal with when we often square a projection operator, which is given by a matrix, that is equal to itself. So the Pauli matrices also, they follow this general computation rule where we have 2 times the imaginary I times sigma z here for sigma x and sigma y. So what we are going to do now is actually to go into the definition of a computational basis and what that means, because that's one of the main building elements in many-body physics. So there are some reminders on matrices here, which you can look up. So I'm not going to do that now. You can look this up. But I want to go to the whiteboard now and look at an example of a computational basis. Because this is, as I said, the building block for most of the things which we are going to do. So let's switch to the whiteboard and then take a quick look at that on a computational basis. So I actually want to set up this a system with the hydrogen-like states. So let's change to the whiteboard. So if you think of a system like the hydrogen atom, we know that, so let's just write this down. Then we know that we have a Hamiltonian, which is given by a single particle Hamiltonian. So I'm going to write operators H with a hat. I'm going to use a low E letter for single particle operators, and then an upper case letter for many body operators. So this is an operator which acts on a single particle state. It has a position X, so it's simply going to drop spin as well. So I'm going to write X vector here, and that contains a kinetic energy term, 2 divided by m, the mass of the electron in this specific case. And then I have the second derivative. And then I have the potential energy, which is given by the Coulomb interaction, which is the attraction from the atomic nucleus. And this is given by the distance. So in this specific case, this now contains a minus sign because it's an attraction given by the atomic nucleus, the number of protons which you have, one for the hydrogen atom. There is a constant K times E squared, and then this is a charge. And then we have the relative distance between the atomic nucleus and this electron. Now, this problem is actually a problem which has an analytical solution. And we know that H acting on this specific state, which we have, and I'm going to write this N psi in terms of alpha, and then I have X here, is something which has an eigenenergy. So this has an analytical solution, and the states here are typically called the hydrogen-like wave functions. I guess you've seen the derivations of this in different courses in quantum mechanics, and the wave functions here are given by an exponential multiplied by a polynomial, which is called the Laguerre polynomial. So you will often see this psi. So I'm just going to rewrite it like this. So this will contain a polynomial of alpha over x. And this is multiplied with e to the minus, and then there's some parameter beta multiplied with x here. And that's the absolute value. So the L's are the Laguerre polynomials. And we know that the energies are also given by analytical expressions. And this alpha is a collection of quantum numbers. So we have N and L, and then so this is the orbital momentum. So N is the number of nodes minus 1 of the wave function. L is the orbital momentum, and M is the projection of the orbital momentum along a chosen z-axis. We are skipping spin for now. So we're going to bring spin a little bit later. But we know that these states here, when we now look at the energies, so we can make a plot now. Oops. Okay, so we have a state with which is normally labeled as, just a moment here, there is sorry. Something happened here. Okay, let me just bring this up. So we would have the lowest lying state with a specific energy. So this has an energy epsilon alpha, which is labeled as a 1s state in atomic physics. So alpha equal to 1s, that means that we have n equal to 1. So this is this number. And it has L equal to 0 and ML equal to 0. So that would be the lowest lying state of this system. Then we have new states. We would have an epsilon 2p, and this is degenerate with a 2s state. So they have the same energy unless you put things in a magnetic field and you lift this degeneracy. If you do this in a many body context, the 2p and the 2s orbitals will change. If you run a Hartree-Fock calculation, they will not be the same anymore, because then you have an interaction. This is the result for a non-interacting system. So non-interacting means that there's only one electron. And we would have the epsilon 2s. So 2s means that we have n equal 2. We have L equals 0, and M and ML equals 0. In this specific case, we have N equal 2, we have L equal to 1, and then we have ML equal to -1, 0, and +1. So these are just quantum numbers. So it means that if you think of this in terms of some kind of boxes you're going to fill in, you will have slots for single electron states. So this continues, and there is an infinite set of bound states for the hydrogen atom. So this system is not fully realistic because the hydrogen atom can actually emit an electron. It can lose an electron, and then it just becomes a charged hydrogen atom, because you have the possibility here to knock out the electron, which is bound by the atomic nucleus, so its motion. But if you give it enough energy, you can knock it out away from the hydrogen atom. And then you have a charged, or you have a hydrogen ion. Now, so in this case, when you solve that problem, you have only bound states. And you have an infinity of bound states. So if you're looking at more realistic systems, you would have to add to the solution the fact that these single electron states do not need to be bound. You can actually knock an electron out. But here, this just surfaces as a computational basis. So what you could think of now, if you look at this, these are the energy states, you could now think of translating this into a computational basis. And that computational basis then is so that you have boxes here. So we have box 1, and that contains n equal 1, L equals 0, and ML equals 0. And that is the box number 1 is the 1s. So now I'm thinking of the way you would present this in memory of a computer. So the next one, box number 2 here, could be the 2s state. So I'm just writing I'm going to use this kind of atomic physics way of labeling the states. So when I say 2s, that defines specific quantum numbers. So you could think of this as an array where you point to other arrays where you have the given quantum numbers. So if you think in terms of programming, you would have a pointer to a pointer, right? So you can even quickly translate this into the way you would lay out the states you're interested in. So what you have next here would be the 2p, but now you have to be careful, because in 2p, we need to make ML equal -1. So this could be slot number 3. And then you have a 2p here with ML equals 0. And this could be slot 4. And then I can have 2p with ML equal to +1. And this would be slot 5. And then you would continue with slot 6, and then you can do the 3s, where you also have L and ML equal to 0. You have only one state. But what happens now is that we have omitted spin as a degree of freedom. So since we have omitted spin, it means that in every one of these slots, we can have one more electron, because the electron can have spin up and spin down. So that means that if we have 6 slots, we can multiply them with 2. So we would have 12 slots for the electrons with the spin as an added quantum number. And you see now that this can just go on till you have defined a computational basis. So note one thing, at the single particle level, we are now constructing what we will call a computational single particle basis. So what we have here is what I will call a single particle basis. And in principle, this one is infinite. Infinitely large. So we have to make a truncation, because we cannot treat infinities in our computers. So this is the first truncation we make. And in many body physics, we always end up having to make such truncations if we start with a single particle basis. The next step then is to use this to make a many body basis. But we need to make a truncation here. So that means when we do this, we need to truncate. To some final. I have some small problems with my iPad now. Okay, there's some final. Let me just final. Let me just write it down here. There seems to be a small delay here in my writing. Let's see, that was better. Okay. To some final. No, sorry for this. It's actually my iPad here, which seems to be causing some problems. Never happened before. Let me see if there is a problem with the, okay. Let me just do a plain template and see if that one changes things. So to some final, that changed it actually, single particle basis. And I'm going to call that one for a number D, and D for the dimension of the single particle basis. And I'm going to use that symbol for the rest of the semester here. So when I have this little d, that is the dimension of the single particle basis. So you could think of now, if you want to describe atomic neon, for instance, if you want to do that, you know that atomic neon with electronic degrees of freedom, it has 10 electrons. So atomic neon then, if you add spin, that would contain the single particle states 1, 2, 3, 4, 5, multiplied by 2 with spin. So if you think of neon as an example for this kind of calculation with 10 electrons, you could now think of defining a basis which now contains the 1s state. There's something which goes wrong with my iPad now and my drawing program here. The 1s. So if I do the neon as an example, I would have the 1s state, which has n equals 0 and n equal 1, and L equals 0 and ML. And if I add spin, what I have now is a spin up case and a spin down case. So I can have 2 electrons here. Then, if I think of the 2 p states, I have a degeneracy of 3 there. So I would have 2p here with ML equal to -1, ML equal to 0, and ML equal to +1. And then I can place 1 electron with spin up and 1 with spin down, and the same here. So I can now start filling these states with electrons. And then finally, we have the 2s, which is now a state which in a single particle basis of the hydrogen type is degenerate in energy with 2p, so it has the same energy. But this degeneracy is lifted in a many body environment. And then I would have a spin up and a spin down. And then we have 10 electrons. And these are typically closed shells. So this is a typical situation, what you see here, of what we could define as an effective Hilbert space. And this is going to define a many-body state. If I go to a simpler system like atomic helium, just to take an example. So if we do atomic helium, and I'm going to make an ansatz for the ground state. So ground state. If I do that, then I could simply think of us having the 1s state, and then 2 electrons, one with spin up and one with spin down. That could be my ansatz for atomic helium, for the ground state. And I could say that, hey, maybe I now just use the 1s states as my way to define the two-body wave function for atomic helium. So the whole thing here, which you see, is that we are using the states, which you see here, as a computational basis. Now, if we go back to atomic helium, what we could say now is that an ansatz for the wave function for the ground state for atomic helium, for electron 1 and electron 2 here, so we have 2 electrons, and I'm going to put a GS here to mark that this is a ground state. So this will be proportional now with the product of 2 single particle wave functions. So I would have the wave function for 1s for electron 1 and the wave function for electron 2 in also the same spot. Here it means that I also need to include spin. Now, the wave function you see here doesn't have the right symmetries. So the wave function needs to be antisymmetric. And for a fermionic system, it has to obey the antisymmetry. I cannot have 2 electrons in the 1s state. I need also to include spin, because else I can have only 1 electron. And if these were bosons, the wave function had to be symmetric. So this wave function, which you see here, is not a wave function with the right symmetry. But this is the way we would think. So if I now make a many-body system, this in this case 2 electrons, I actually can write that as a product of 2 single particle wave functions. So this is the idea. You have in principle, we have an infinite basis, which we have here. We truncate that basis. That basis is still an orthogonal and normalized single particle basis. And I'm going to use this single particle basis to build a many-body basis. This is the basic recipe in many of the many-body methods, which we are going to study here. So just keep this in mind. We have just defined one type of computational basis. If you think of another famous basis like the harmonic oscillator in 1, 2, and 3 dimensions, that's another example of a computational basis. So the choice of computational basis depends on the type of physics problem you have. So if you're dealing with atoms, like the helium atom, neon, or whatever, then you wouldn't start using a harmonic oscillator, because the harmonic oscillator goes like e to the minus x squared, which means that the wave function would die out quickly. Whereas in atomic physics, it has a tail which goes like e to the minus x. So if you want to build e to the minus x with a harmonic oscillator basis, you would need many more harmonic oscillator functions to describe that basis. So remember that you can always define a new orthogonal basis in terms of another orthogonal basis. So one of the mathematical principles results which we're going to use now is to use an orthogonal basis to build another orthogonal basis via a unitary transformation. So this is going to be an essential part in what we are going to do. So what I will do now is actually to bring back the slides, because there are some discussions about orthogonal states, which we then use to build a new basis. But just to remind you of the orthogonal states. So one of the things which we can do now is to define a new basis, a new single particle basis, which is given in terms of a state psi, and let's call this alpha, and it depends on x. And this contains now in principle a sum, which runs from 0 to infinity, and there are some overlap coefficients. So this would be an overlap coefficient between I and alpha. And then I have my original basis, which is an orthogonal basis. And this basis is now given in terms of these indices I, and I have x here. So we have assumed that this is an orthogonal basis. Now we know that these coefficients C, they are just the overlaps between these two states. So the C of I alpha is actually equal, and I'm going to write this in a more compact way, this psi of alpha with phi of I. And this is actually an integral. So the calculations which we are going to deal with in this course is actually to find different recipes which allow us to find this coefficient C I of alpha. Because normally the quantity which you see here, this specific quantity, so this has changed a little bit. Okay, it should, okay, let me highlight this one. So the quantity you see here is normally unknown. If you have it, you can calculate the coefficients, but many of the many-body methods deal actually with you having a recipe to find these coefficients. So just keep in mind that we have made a truncation, but the basis is still orthogonal, and we can use that one to expand a new basis. And essentially all the many-body methods, they use these kind of properties of orthogonal basis states. So it's important to find a computational basis, and then we use that one in the different many-body methods. So let me bring you back to the slides, and we are going to repeat these things because some of these basic things are very important. So one computational basis which we can define, which is the typical one you would meet in quantum computing, where you represent qubits, is a basis like this, 1 and 0. And we know that this basis has been orthogonalized with respect to this state. So we have only two states now. In the previous case, we had for the hydrogen atom, we had an infinity of basis states, and we made a truncation. Here we have only two. This defines our space. And these states here are also eigenstates of the Pauli sigma Z matrix, but not of sigma X and sigma Y. So what we can do then when we have this, we can now calculate the outer product, and we have the identity relation here. And this is given by the outer product. And you see now, if you take the first one, that gives you a matrix, which is a 2 by 2 matrix. So this is just us applying the outer product. And then we have the other state, which gives us this one. Now, since these two guys are orthogonal, there is no cross term here. And this is the matrix. So this is just the identity matrix, as you can see. However, each one of these serve as a projection operator. So if I act with this one on one of these states, it's clearly going to be, if it acts with this one on that state, it's going to give us 0. And I can define a space here. So my full Hilbert space given by these two states, which is defined by this completeness relation I, is given by this P plus Q. So P projects out the state 0, and Q projects out the state 1. So this is the simplest possible basis we can think of, but this can also be a computational basis. So a small digression, which is important if you're going to do quantum computing. When you do quantum computing, you have to deal with realistic many-body systems, and these are complicated systems. And what you often are looking after are many-body systems, real systems, which have some states which are well-defined and have a long lifetime, because you can often use these as candidates for making computations. So you would take a real system and look at the, let's say, the two lowest lying states. It could be the ground state, and it could be the first excited state of a system. And then you would label one as 0 and the other as 1. And you would use these as computational basis states. So this is what you would do experimentally if you want to build quantum gates and quantum circuits in order to make quantum computations with real devices. For us, in theory, we can just think of this as a specific basis we just cooked up. But you could think of this as something which represents the two lowest lying states in a many-body system. This can be a complicated many-body system, or it could simply be this 0 and 1 and 1. That could simply be, if we think of this hydrogen atom, as the 1s and the 2s state. So the thing I want to have you with me is that we are free in a way to define the computational basis. And you see that the computational basis here, the simplest possible one we can think of, a two-level system, has now an orthogonal basis, 1, 0 and 0, 1. And when we define these operators here, these are operators now, represented by matrices. When they act on these states, they project out some specific states. So P acting on 1 is 0. P acting on 0 gives back 0. So that projects out that specific state. And then you know that in quantum mechanics, you can make superpositions. And you know that you can now find a superposition of these two states. So when we have constructed an orthonormal basis, if you go back to what we put on the slide with the expansion in terms of an orthonormal basis, this will be a new state, which also would be orthonormal. But it has a different normalization coefficient, which is now given by this alpha squared plus beta squared. But that still has to be 1. So when you make this transformation, this is normally given by unitary transformation, then the orthogonality stays the same. And if the basis is normalized, the new basis is also normalized. But the normalization criterion here is that alpha squared plus beta squared is equal to 1. Then, if I act with this projection operator we defined up here, this operator here, and this operator on that specific state, you see that this one projects out the 0 state, because the 1 state is basically, if you take 0 and 1 here, that gives you 0. So that projects out the 0 state, and the other one projects out the 1 state. This is often used in quantum computations when you want to make a measurement, because then you project out a specific state. So I wanted just to bring in this as a small digression, because it links this discussion of computational basis to many different types of applications. Does that sound clear? Is it okay? So I hope you see the reach of what we're doing, but I'm going also to repeat many of these things here. And then there's another thing which we can do now, and this is the last thing we're going to do, is to define what's normally called the density matrix of the states. So this is another quantum mechanical quantity, which is very useful. So that is actually the outer product of the new basis. And the outer product of the new basis simply gives us this. And if I take the trace of that one, that gives me the normalization factor again. So modern quantum mechanics is also very much defined in terms of density matrices. So density matrix is a quantity which is used quite often, in particular in quantum computing. Now, what you will find here are some other matrices, but we're just going to leave them. And the thing which I wanted to bring up now, before we end, and this is where we will start tomorrow, is that when you look at the state which we have, when I mention spin together with the hydrogen-like wave functions, that's actually the total single particle wave function is a tensor product between the spin part and the spatial part. So when we are defining a, let's say a two-particle state, that's actually given by the tensor product of two single particle states. So just to remind you of tensor products, because we will pick that up tomorrow, and tomorrow we're actually going to define expectation values and to calculate the set of the wave function for two electrons, the helium atom, and then we are going to calculate the expectation values of the energy, but then we need to remind ourselves about what a tensor product is. So if you have two states, X and Y, the tensor product is often written like this. So what it means is that we have this. So think of this as the solution to the hydrogen atom problem with only the spatial degrees of freedom. And think of this as spin. Then your single particle wave function is the tensor product of the spatial part with the spin part. So the 1s electron here has a spin up part and a spin down part. The 2s electron has a spin up part and a spin down part. But normally, this kind of mathematical operation is hidden. It's hidden in this more compact notation because we get lazy at a certain point and we don't write this tensor product symbol, but we write it like X and Y. So what you will see then is a state which now contains the spatial quantum numbers and the spin quantum numbers. But what it means mathematically is that actually we have the tensor products of different states. And this is where we'll stop today, because you can also go on and you can make a two-body state. And this could be a 2-qubit state based on a 1-qubit state, just to give you an example. And you can make these different states, which also are orthogonal, by just building up these different tensor products. But typically, what we would do now is to just write it in this compact way. And later, when we make a table for computations, this 0, 0 becomes state 1, with 0, 1 becomes state 2, state 3, state 4, and so on. So I just wanted to remind you of that, because when we often look at notations in textbooks and so on, you will see this compact notation, but what it actually means is that the tensor product between different states. And this is where I wanted to stop today, so that we can then move on to the first example tomorrow, which will be the helium atom. So if you have time, take a look at some of the material here on Hamiltonians and more definitions, because I will cover that stuff tomorrow in the lecture. So I hope it wasn't too simple, or I just wanted to bring back some linear algebra topics, but also the basic definitions which we will be using over and over again.